For 4.6 billion years, the Sun has continuously radiated extreme heat and light in every direction without a single interruption. Powering a star of this scale using standard chemical reactions is mathematically impossible. If the Sun were a solid ball of coal, it would be reduced to ash in just a few thousand years. To find the true source of this energy, we look inside the atom. It is mostly empty space, but at the very center is an incredibly dense nucleus that contains more than 99.9% of the atom's total mass. Deep within the solar core, atoms are stripped of their electrons. This creates a dense plasma of individual hydrogen nuclei, which are solitary protons. A star's multi-billion-year lifespan is a direct result of how these microscopic, dense proton cores are manipulated under extreme conditions. Protons have a positive electric charge, causing them to violently repel one another when close. This repulsion creates an invisible force field known as the Coulomb barrier, which prevents protons from making physical contact. Inside the solar core, crushing gravitational pressure and heat near 15 million degrees Celsius grant the protons immense kinetic energy, allowing them to race through the plasma. This curve plots the potential energy between two nucleons. At a distance of 0.8 femtometers, the energy drops sharply. If protons can be forced into this specific range, a stronger force takes over. The kinetic energy of the collision drives the protons past the barrier. Within 0.8 femtometers, the strong nuclear force activates and snaps them together. This physical victory of the strong nuclear force over electrostatic repulsion is the prerequisite spark that ignites thermonuclear fusion. The proton-proton cycle is the mechanical blueprint that builds hydrogen fuel into heavier elements. In step 1, two protons fuse. To stay joined, one proton morphs into a neutron by ejecting a positron and a neutrino. This creates deuterium. In step 2, the deuterium nucleus rams into a third proton. This merger forms helium-3 and emits a high-energy gamma ray. That pulse of radiation is the actual high-energy light that will eventually escape the star and travel through space to reach Earth. The final step occurs when two separate helium-3 nuclei smash together. They merge into a single, highly stable helium-4 nucleus. Helium-4 only requires two protons and two neutrons, so this final collision ejects two leftover protons back into the plasma to fuel the next cycle. The net result of this engine is consistent. Precisely 4 hydrogen protons enter the cycle, and one stable helium-4 nucleus is produced. If we weigh the 4 starting protons against the single helium-4 nuclei they created, the ledger no longer balances. The finalized helium-4 nucleus weighs measurably less than the sum of the 4 protons that built it. This missing matter is known as the mass defect. In a closed system, physical matter shouldn't simply disappear into nothingness. We must account for where that material vanished to. The answer lies in the principle of mass-energy equivalence. According to E equals mc squared, that tiny destroyed fraction of mass was entirely converted into 26.7 mega-electron volts of pure energy. This chart shows the binding energy per nucleon. As light nuclei fuse into helium, they move up this steep curve, becoming more tightly bound. The energy equivalent of the missing mass is what holds the nucleus together. This outward explosion of converted energy perfectly counteracts the crushing inward gravity of the star, preventing it from ever collapsing. The literal destruction of microscopic mass is the ultimate engine of the universe, providing the light that sustains all life.